and Sn, we can get symmetric power. Yes, we can say, okay, so if x2 is a complex surface, then we take Sn x2, and then this is smooth. And if you have a Kessler surface, local forms can we have a form on a smooth piece of this variety, and then by this trick we can extend to the whole thing, and it is non-single. So in this way we obtain, so the first series is Sn K3. Yes. So this is a series of two n-dimensional manifolds, and second is series obtained in a similar way from A2. It is slightly different, so we take Sn of A2. So this is two-dimensional torus. So we take maybe I should put G2 torus. Then map to G2, and then so this is a fibration with a fiber, let's say Xn, and this is smooth fiber. This is second series. Image of a point P. Fibers are isomorphic. This is pre-image is just sum of points. This image is certain. And these are two infinite series. Infinite in the following sense, that for each such variety, you have a similar deformation space. But the interesting point here is the dimension of deformation space is 21. 20 plus 1, 20 for K3, and one extra dimensional deformation. And now, though these 20 parameters, so 20 parameters are just symmetric powers of Kessler surfaces, and one parameter is sort of mysterious, even more mysterious deformation. And again, plenty of here, again, the structure, so now we have space of dimension 20 instead of 21 dimensions, so the space will be 21 dimensional, and exactly the same picture of projective and kind of hyper and Lagrangian fibrations.
So what does it mean? So for this deformation family, you have a kind of global parity theorem. So where do you get an extra parameter? So then deformations are no longer symmetric powers, right?
No longer, yeah. Extra parameter is just by one parameter is added. It's like
just
from diagonal.
Sort of global parity theorem.
Yeah, it's like from diagonal. So for example, if you have S2 of Kessler, yes, you have pre-image of diagonal. When you look at S2 of K3, there is on a product of two K3, you have a diagonal, which is certainly not in any of them. Yes, this is but then you blow it up. It's codimension 2. You blow it up, you obtain something like. So in dimension 2, what I discussed here is exactly blowing up of the diagonal to make it smooth. Diagonal, the quotient by diagonal is not smooth. You blow it up. So over each point you add P1, you obtain a divisor. So it's very clear, and then now you deform a surface, you have a deformation which destroys this divisor. It's not any longer a complex of variety. That's what happens when you move out into this form. And the same picture is here. So exactly the same picture. So meaning deformations, just slightly different computations of the conics, or what is the quadric and so on. And then So, and so therefore there is a like 6, 7 dimension. Here, 21 dimensional family. So for each n you have, kind of here you have 21 dimensional family. Here, let's say, if you think about family, all this complex, yes, everything what can be connected by deformation. Okay, and here we have 7 dimension, and then we have 2 varieties already. Varieties in dimension 6. And as it was shown quite recently, only recently, they also can be deformed into, they also have similar quadric and so on, but the fact that they can be, that actually this property d squared equal to 0 provides with some kind of existence of Lagrangian fibration was proved quite recently. Maybe this or maybe last year, I think it's 2018 only, because they have a completely different description in terms of moduli space. And nothing else exists, nothing else, yeah. So at the moment. So the main goal of the theory at the moment is kind of negative. Show that it's also. Basically that there are no other projective hyperkahler varieties with this property. And in fact, certainly the idea is to go through the first to understand Lagrangian fibration. What kind? So let's see what are Lagrangian fibrations and how many of them exist, and maybe you can get some restrictions. And in this direction, oh, okay. So in this direction, there are several results. So maybe I'll repeat. The goal is to classify. And this is the last maybe possible kind of class of varieties in general which can be reached. That means trivial canonical class is certainly the boundary of our kind of expectations, where we can say something in general. Beyond, we have a huge ocean of varieties of general type. There is no hope. We can discuss individual varieties. We can discuss and say something about individual varieties, but almost nothing in general. And here, at least, there is a hope that there is a classification, and potentially this is a classification. Since, despite of the efforts, 30 years efforts, nothing else was constructed. So therefore, there are the following theorems. So we have a Lagrangian. So if xn is hyperkahler, x2n is hyperkahler, and this is Lagrangian. And this is in fact, any map. And assume that it has a map into a smaller dimensional variety, subjective map. Then it is a map into then the fibers it goes. That's a very general statement for hyperkahler. So if x to n maps to b, dimension b prime less than to n, then fibers, generic fibers are story. Maybe not Lagrangian, but here. So if you have, so therefore, what we are looking is, so if you have a Lagrangian map, then this Bn is, if Bn is smooth, then Bn is projective space. That's not so sure. to actually complete this. To shoot one and completed it, but some results were known before. That is always a fibration over projective space.